a lot of what we're going to talk about today, you can already know. But let's go through it because Mr. Passwater has a wonderful way of expressing things. So on the first page, in the big box there where it says transformations of functions, he talks about what you already know. If you have, let's just say we have x squared. If we put a plus 5 on the end of that, what does that do? You know this. It moves it up 5. It's called a vertical translation. And if it's a plus 5, it goes up, and if it's a minus 5, it goes down. So a vertical translation. The picture is literally picked up and moved vertically. If you put that plus 5 inside the parentheses with the x, so it's part of the squaring thing, then what happens? This one would go 5 to the left. This is a horizontal translation. And you'll discover that when things are happening to x, this is vertical, so this is happening to y. But when things are happening to x, it's always the opposite of what you think. So when I would look at this, I would think, okay, I'm adding 5. I would go 5 to the right, but I don't. It's the opposite. It goes 5 to the left. A horizontal translation. Now, what happens if you put a coefficient on the problem? What impact does that have? Like this, what does that do?
Does it divide everything by 2?
Actually, this one doesn't. My example is a little bit confusing because of the way I've written it out. Let's try this. Let's say our function is f of x. 2 times f of x. That 2 is what we call a dilation. It doesn't move the picture. It changes its size. And when you put a multiplier out in front, it actually multiplies the height. So that's a y thing. It multiplies the height. Obviously, this one, whatever that original picture looked like, this would be 2 times as tall. So if this was a little like thing like this one would be twice as tall, right? Now, if you put a 1/2 here, it's still a vertical thing, but instead of stretching it, it is compressing it, shrinking it, right? So this guy out here in front of the function itself is going to impact the height of the problem. It's called a vertical dilation. If you put that 2 on the x itself, then it becomes a horizontal dilation, right? It's going to stretch or shrink this way. And remember what I said about things on x? They do the opposite. So this is actually going to divide the x's. So if the original picture, let's do a really simple picture. If that was the original picture, then this would be this. Half is wide. So instead of being at 2, 0, you would be at 1, 0. Putting a coefficient somewhere in your problem affects the size, not the location, the size of the figure. Okay? Putting it out in front is vertical. Putting it on the x is horizontal. Now, one more quick comment. If that coefficient you put in there happens to be negative, then not only does it change the size, but it also reflects it. If it's out in front, it reflects it across the x-axis. This is upside down. If it's on the x, it reflects it across the y-axis. All right, we good with the basic rules? Okay, let's look at example 1 down at the bottom then. All right, so G is 2 times function f plus 1. Describe the transformations of the function. All right, so what are some things that are happening? Let's make a list here. What is one thing that's going to happen to the picture? What? Up 1. Every point's going to go up 1. What else? Gonna go right 3. So this picture's actually gonna move. We're gonna cut it out, paste it down somewhere else. What else? One more thing.
Multiplies the height by 2.
Multiply the height by 2. So we're gonna multiply the height. You might want to think of those as y's by 2. So for example, I don't have function f, I don't know what function f looks like, but let's say function f contains the point, let's say 1, 6. All right, that's on function f. What would be the corresponding point on function g? Well, these two are going to affect your y coordinate. Would you agree with that? This is going to affect your x. So the corresponding point for g is going to move right 3. So this will be 4. And we're going to multiply the height by 2 and then go up another 1. So this will be 12, 13. So if we had an original picture, some points on the original picture, you could do these things to those points and end up graphing a new picture. Is that good? Sylvia's nodding. Got it? All right, let's look at example 2. Let n be a function that is a transformation of the function m, so that n of x is negative 4m to x. What transformations have happened? What's happened? Reflect across the x-axis. And that is a very mathematical way of saying we're going to be upside down. So whatever was pointing up in the original picture will be pointing down. All right, what else is going to happen? Heights by 4. And again, our height is y. And then divide the width by 2, and the width is the x's. So we're going to divide the width, which are the x's, by 2. Is that all right? Let's practice that with a point. So let's say that our original function has the point of, let's say, 4, 7, okay? What would be the corresponding point for our function n of x? All right, let's see. So this is going to affect y. This is going to affect y. And this is going to affect x. All right, so our x coordinate was 4. Our new x will be 2. Our original y was 7, so we're going to multiply that by 4, get 28. and then reflect it, so this will be negative 28. Is that okay? All right. Now example 3 actually gives you a picture now, and then asks you to do a transformation on it. So can we do that? For f of x, what are the points in the original picture? The key points, not all the points, but the key ones. Negative 3, 3, and 0, 1. Don't let me make a mistake. Looks like the top of that is about, what, 1.5, 2.5? 3, 1, and 5, 1. Does that look okay for key points for function f? Now, which ones are you gonna plot then for function g? Well, what are we gonna do? What does this transformation do? Our x's are gonna do what? What? Wait, make sure we're looking at the right picture. We're doing example 3, Leo. And example 3 says f of x plus 3 minus 4. This is our transformation. All right, so what's happening? The x's are doing what? Left 3, so we're going to go left 3. All right, so if I take all these and go left 3, they're going to be, left is that way, right? Minus 3. So this is going to be negative 6, negative 3, negative 1.5, 0, and 2. How does that look? Did I do that right? Left 3. What's happening to the y's? Down by 4. So negative 1, negative 3, negative 1.5. None of my arithmetic. Down 4 would be negative 3, negative 3. That look all right? Now, if you plot those points on your graph and connect them so that the first 2 make the segment, the next couple make the semicircle, and then you have your little horizontal line, you have to be able to get it. Yes.
Is this for example 3?
What?
Is this for example 2 or 3?
This is example 3.
Those are the points for 2.
No, example 2 has no graph.
Oh, the graph is a.
Example 3 has f as its graph.
Oh,
So the picture, that top picture goes with example 3,
okay.
and the bottom picture goes with example 4.
Okay.
Okay? Example 2 has no picture. All right, are you with me here? Did you plot those points? Did it come out looking exactly like his, except left 3 and down 4? Did we change the size or shape of that in any way? No, because the only way to change the size is to put what into your, what do you have to do? You need a coefficient, need a multiplier. If you're just adding and subtracting, you are just moving it around, right? All right, let's try example 4. Now, example 4 talks about that picture right there, H. Says it has a hole at 4, where x is 4. It has 3 line segments. You see them there. Sketch a graph of K, where K is negative h to 2x plus what? Alright, so what is going to happen to all of our points now? each point is gonna have to be moved, changed, how?
Reflect across the
Gonna
axis.
reflect across the x-axis, or think of it as multiplying y by -1. Making y negative, changing the sign on y. We're also gonna go up 1, right? Would you agree with that? So these are gonna affect the y's. And then what's gonna happen to the x's? Yeah, the x's are divided by 2. The width of the picture is gonna get scrunched. It's divided by 2. So you can either write down all the points, like I did on that example, or we can just do one at a time here. The first point for that first line segment is -4, -3? No, yeah, -4, -3. So that's gonna become -2. And then this is going to get multiplied by a negative, so it'll be 3 plus 1, 4, so -2, 4. So I'm gonna plot that point. Does that make sense? That yes, John?
And you do PEMDAS with this, right?
Yep,
Like, yep,
you sure
it's the
do.
Same thing.
You sure do. And then the second, the one that connects to, is at -2, 1. So what's gonna happen to -2, 1? Well, it's gonna become -1, and then 0? Let me try that again. So I multiply by -1 and then add 1. Yeah, is that what you got? -1, 0? So there's my first line segment. Now, let's get that hole involved. What are the coordinates of the hole? Oh wait, no, the next point, I need the next point. 0, -2. So what's that gonna become? What happens to the x? Stays 0, yep, stays 0. This becomes positive and goes up 1, so 0, 3. All right, let's get our hole now. Our hole is at 4, 2. So that'll become 2, -1. Keep an eye on my arithmetic, is that right? So 2, -1. And then I'm finally gonna end at 6, 4. Which will be 3, -3. What do you think about that? Good? All right, example 5. Go back to example 3, which was that picture there, that semicircle thing. And it says the domain is -3 to 5. All right, look at the picture. Would you agree with that? That the domain is -3 to 5? And the range is 1 to 3. Does that make sense to you when you look at it? Now, without looking at the picture you drew, can you tell me what would be the domain and the range for this transformation? Of course you can, because we know what's happening to our x's.
Left 3.
Left 3. So aren't these the x's right here? So in the original, we went from -3 to 5, so where are we gonna go in the transformation? -6 to 2? Sure, everything just got backed up 3. Now, what are we gonna do to our range? We're to double it and subtract 4. So our range, if we double it, it would be 2. And then subtract 4 would be -2. Double it, 6. Subtract 4, 2. Is that good with everybody? Now I want you to notice something. How, wide was the original domain? X's were how wide? Yeah, how far? 8. Look at the transformation. How far did we go? 8. That makes sense, right? Because we took the picture, picked it up, and shifted it. Now look at your range. What's the vertical distance in this? 2, but this one is 4, of course, because you doubled the height, right? So that, of course, would change. Okay, now I'm gonna stop there for a second and have you go to the back of that page that says building a library. So there are 6 of these guys that we need to make sure we have a grip on. These are often referred to as parent functions. They're just the basics. All right, so let's fill in some of this information for these guys. Okay, so this is your basic linear or identity function right here. You don't need to plot any points if you don't want to. Can you tell me the domain and range? What's it look like? Do you know what this looks like? This right here, right? So what's its domain and range? -infinity to infinity. Completely unrestricted. It's a wonderful, wonderful function. X-intercept and Y-intercept are both at the origin, right? 0, 0. And then what do you think about increasing and decreasing for this function? Remember, when you make that decision, you're always moving left to right. So what do you think about this guy? Always increasing. So he is increasing on the interval -infinity to infinity. That's what that means, increasing on the interval, right? The interval, and the whole dang thing is increasing, so it's -infinity to infinity. Good. Now, what's the next one look like? I heard someone say it, I think. It's a V, right? What's his domain? -infinity to infinity. Be careful, what's his range? 0 to infinity, and that 0 needs to be bracketed, right? So that's 0 to infinity, that's his range. Once again, the X and Y intercepts are the same point, the origin. And now what can you tell me for this guy about increasing and decreasing? He's increasing from 0 to infinity, and he's decreasing from -infinity to 0. Now, this isn't a huge deal, and I don't want to cause a bunch of confusion, but these are going to be open intervals now, because 0 is where we're really changing direction, so we're not increasing or decreasing at that point. So we're just saying, starting at zero, you can give that like an open dot. That part's going up, and this part is all coming down. Okay, are we all right with that one? What's this look like? Parabola, please don't say a U. That's a parabola. And would you agree that everything you wrote down for your absolute value applies to this? Yeah, so everything's the same. We're decreasing and increasing on the same intervals, we have the same domain and range, everything's the same. Good? What's this guy look like? A little squiggle, hula. Hula. Little squiggle like that. Domain and range. Negative infinity to infinity for both. For both. X and Y intercepts are both the origin. 0, 0. And what do you think about increasing and decreasing? Remember, we're moving left to right. Always increasing. So we are increasing from negative infinity to infinity. We are never decreasing.
Can we just write none? Or for
For-
decreasing?
Yeah, you can just write that. All right. What's this guy look like? Anybody know? This is your square root function, your root function, Charlie?
It looks like a parabola, but it's to the side and only one half of it.
Exactly. Because, Charlie, if we included both halves, it would not be a
Real number.
function,
Right. Yeah.
right? So we've got to include only the top half of the parabola. Does it make sense to you that if squared is a parabola opening up, its inverse is gonna be a parabola opening sideways? But like Charlie said, you can't include this part because then you wouldn't be a function. So it's only the positive half. Domain? 0, and that 0 is included. That's your domain. And actually, is that also your range? Yep. X and Y intercept, again, the origin. And what do you think about increasing and decreasing?
It's never gonna decrease.
Never, this is going up, this is increasing, but be careful, it is increasing on this interval. Okay, it's not negative infinity to infinity because this function doesn't exist on the left side. So you are increasing on its entire domain, which is 0 to infinity. So all these have names. This is your linear or identity. This is your absolute value. This is your quadratic. This is your cubic. This is your square root. What do we call this? Reciprocal. This is your reciprocal function. What's he look like? He is more difficult.
It's kind of like the square root function, but kind of sideways.
Yeah, there are some similarities there, I guess. Here's the deal. We have a vertical asymptote at 0. Why is that?
Because you can't come out by 0.
X can't be 0. But we also have a horizontal asymptote at y equals 0 because in that fraction, where's the biggest power? In the denominator, right? In the denominator, yeah, that's the first. So whenever the biggest power is in the bottom, you have a horizontal asymptote at 0. if X is positive, would you agree Y is positive? So we'll stay in quadrant 1. But if X is negative, Y would be negative, so we also have a piece in quadrant 3. Domain.
Negative infinity to 0,
Negative infinity to 0, don't include either one of those things.
then 0 to infinity.
And then 0 to infinity, beautiful. That is the domain. Would that also be the range?
Yep.
Yep, it sure would be. So the domain and range are the same, they are this. How about intercepts? None. No X, can't, you got asymptotes there, you're not touching the X or the Y axis. How about increasing and decreasing? Remember, we're going left to right, left to right. Isn't it always decreasing? And it's decreasing from negative infinity to 0. This whole part is decreasing. And then it's decreasing again from 0 to infinity. All right, let's look at the back of that page. Check your understanding. So considering these 6 as our group of parents, which parent functions demonstrate a constant rate of change? So which of those up there, if any, singular or plural, which are a constant rate of change? Linear. Linear. Isn't that what makes a line a line? Rate of change of the slope is constant. Good. Now, this one has a constant rate of change over here and a constant rate of change over here, but they're different, right? This one's negative and that one's positive. So that's the only one. Identify the parent function. Okay, so A is which one of these up here? A is a version of reciprocal. B is a version of, watch it, cubic. Right? Look at it. Tricky. Now look at the whole thing, right? That would be your cubing function. And then C is a version of the absolute value. So these are just transformations. So C is going to be some V shape, right? Shrunk or stretched or moved around a little bit. All right. Part 3, you and your partner figure it out. You've done this before. Determine if the relationship is linear, quadratic, or neither. Go ahead, do it. What did you come up with? Yeah, oh no, we got class going on here. What'd you come up with? Anything? What'd you think about A? Quadratic. And how did you know? What was your thinking? What did you do? It's a good question for, unit 1. What did you do?
Narrative changes constant.
Yeah. First of all, I loved that the X's were all evenly spaced, so I could make a conclusion based on what was going on with the Y's. And the rate of change, the actual change in the Y's was -2, -4, -6, -8. That's a linear change going down by 2's, so that makes it quadratic. Very, very good. Did anybody do second differences? You can do second differences because those X's are evenly spaced. Yep, good. What did you figure out for B? Did you get neither? Or did I make an arithmetic mistake? I actually found the rates of change. So I did, so for the first one, I got 8 over 0.5. Is that what you got? Which is 16, okay? And then for the second one, I got 16 over 1. But for the third one, this is gonna be embarrassing if I messed up my math, but I got 6 over 0.5, which is 12. All right, so what's happening here? It's neither, because if it were linear, that wouldn't be a 12, that would be a 16. So that one was a neither. Okay. Number 4, investigate the range of each parent function below. So, all right, so just, this is sometimes called the identity, the linear. All right, and then order the ranges from least to greatest. Okay, let's do that. So we're finding the ranges from 0 to 1. Share your thought. Please tell me you have a thought. Share it.
They're all the same but reciprocal.
They're all the same, but reciprocal. Charlie?
I don't agree with that.
You don't. All right, let's hear your thought.
I think the square root function and the quadratic function are the same because they're only from -1. Sorry. Actually, wait, never mind. I thought it was -1 to 1. That was right.
Yeah, okay, so you're good?
Yeah.
We're gonna go back and agree with him?
Yeah.
Okay, what do the rest of you think? Think he's right? Okay, so you got the whole group, and then you got the reciprocal function. Which one's bigger, the group or the reciprocal function? The reciprocal function? Because from 0 to 1, you guys, right here, isn't the range gonna be infinite? Right? right? So that's gonna be bigger, yeah. Good job. All right, now let's go back to the regular notes and take a look at example 6. So we're back in the regular notes, doing example 6. I don't think you're gonna have any trouble with this. I want you and your partner to see if you can figure out what the heck is going on. So example 6 uses this table. So this table is a value for function p, whatever function p is. H is a transformation of p. So you know what's happening to p. Now you gotta somehow figure out, okay, what's happening to h. All right, so take a second, see if you can figure that out. This was a question on the exam last year, one like this. So let's see if we can sort it out. If you think you have an answer to these, one or more of them, bring it up, put it on the board, so I want to compare different answers, see what we come up with. Evan, you guys got some action going on over there? You got figured out?
Still working.
Okay. Cole, what about you? You got a thought? No? No thought? Olivia? You got answers? Put them up there. Please don't make this hard, guys. It's not hard. Think about it for a minute. Let's see what Olivia got. What do you think? Anybody get those? I see some racing going on back there, Lydia. I agree with you. You want to tell us? Let's just start with that first one. H of -1. What did you do, Lydia?
I put -1 times 2.
So she evaluated, okay, here's H right here. So when it says find H of -1, doesn't that mean we need to let X be -1. So then what does this become? 3p of -2 minus 1. But this is in our chart. P of -2 is 1. So 3 times 1 minus 1, that's how she got 2. And then, for the second one, she did the same thing, but she let x be 2. And plugged in 2 for her x's. And then she plugged in 6. What do you think? All right, let's look at example 7. 7 does not have a picture or anything, it's just 7 is all there by itself. We got a function g, we got 3 transformations in this order. So if g of x is this, can you fill in the numbers? Can you fill in A, B, and C? What are they? Okay, a vertical dilation by a factor of 4. What does that mean?
Coefficient of 4.
Means we're multiplying the height by 4. And where does that show up? A, B, or C? F. Would you agree with that? Okay. A vertical translation by -7. Pick your picture up, drop it down 7. Where does that show up? C. Alright, so A is 4, C is -7. Now here's the tricky one. A horizontal dilation by a factor of 3. Now, this meant the height was being multiplied by 4, right? So I need to multiply my width by 3. What am I gonna put in here that's gonna end up multiplying my width by 3? 1/3, yeah. Yeah, remember this number divides your width. So dividing by 1/3 would give me multiplying by 3. So A is 4, B is 1/3, and C is -7. Yeah,
Can you go back to 6 and do B and C? And just, I don't know how to get the number for P. That's my question.
okay, so if you put in 2, then this becomes P of 4. And in my chart, P of 4 is 3. So this becomes 3, times 3 is 9, minus 1 is 8. Right? Remember, your chart, these are your x values, and then these are your P of x values. So if x is 0, P of 0 is -1. Right? Yeah. All right, almost done. Number 8. Now we got another chart. Okay. All right, let's build our equation like we just did. So what is our equation for k of x going to be? Can somebody tell me? A, H, B of x plus C. All right, what do we know? What's A?
2.
A?
Oh, sorry. I think just 1.
Example 8. We have a vertical dilation of 3.
Oh, my bad. Sorry, I didn't see
It's
that.
okay. So we have 3 here. And then we have a horizontal dilation by a factor of 1/2. So this will be 2. And then we have a vertical translation of 1. Does that look okay? Chris, you awake back there? Okay. Now, somehow I have to find, all right, so this is my function k. Now I need to find k of -6. So I'm gonna do exactly what Lydia did. This is gonna be 3h of -12 plus 1. Hopefully, -12 is in my table. It is. So h of -12 is 1, so this is 1. So it looks like my answer's 4. Would you agree with that? I'm gonna save the last one for tomorrow. So we'll stop there. A little bit more work to do here. So I'll be assigning that homework tomorrow. So if you want to go ahead and get started on it, you sure can. But I'm not gonna assign it